So welcome everyone, and thank you for joining us virtually for the latest version of the Variant Effect Seminar Series. My name is Jan. I'm a member of the VEST Organizing Committee, along with Adrini de Souza, Ohana Bezerra, and Mariano Martin. And we have three new members, Ziyi Dai, Christian McDonald, and Matteo Cajada. These seminars are made possible with a lot of support and help from Laura Muffley and Alex Hopkins, among several others, and our sponsors, the Atlas of Variant Effect Alliance. As a reminder, we're always on the lookout for potential speakers. So if you know or are interested in presenting or or sharing your own work, feel free to submit a speaker nomination form. As usual, before starting the presentation, I have a few housekeeping items to mention. Each talk is around 20 to 25 minutes, but there should be time for questions. Please post those questions at any time to the Zoom Q&A, and we'll read them to the speaker at the end. If you have additional questions at the end and you're an AVE member, feel free to visit our seminar series Slack channel for more discussion. And finally, we're posting updates on our Twitter account, so be sure to follow us there. You can catch previous seminar and today that have been recorded on our affiliate CMAP YouTube channel. So don't worry about trying to copy the URL. They will be posted in the chat. All the details of the seminar series can be found on our website, including a regularly updated schedule of upcoming speakers. For the last housekeeping item, this is really an issue, but as a reminder, please be considerate when posting comments and questions. We expect everyone to be respectful and use welcoming and inclusive language. Our first speaker today is Jingyou Rao. Jingyou is a computer science PhD candidate in Pimentel Lab at the University of California. Her research focuses on building experiment-driven statistical tools for perturbation experiments, including deep mutational scanning. Jingyou, whenever you're ready.
Yeah. Okay. Thanks for the kind introduction. Good morning, everyone. From California, I'm Jingyou. I'm currently a PhD student in Pimentel Lab at the Department of Computer Science at UCLA. And today I'm going to talk to you about my previous work, which is modeling growth-based mutational scanning counts with Rosace. So I'm going to divide this presentation into three parts. First part is the motivations of why statistical inference is important for deep mutational scanning screens. So the goal of mutational scans is to map between the sequence and the function. So if we, from the perspective like a variant effect predictor, it would be like a function like one-to-one mapping, because we input into the protein amino acid sequence, and then we get the output of a protein functional pathogenicity of the variants. Right? But the reality of the mutational scan is that we are actually measuring some sort of fuzzy effects, which is not going to be a one-to-one mapping. And there are many sorts of variations in DMS, right? Some are biological variation that we actually want to represent in the data, which can be like cell-to-cell difference of protein function. But there are also a lot of technical variation that we don't want in our like final effect estimate, right? So for example, if we can like group different kind of replicates, there will be experimental replicate that when you introduce your variant library into the host, either cells, bacteria, virus, or yeast, you're in general generating some kind of variation. And when you're doing a selection based on a phenotype interest, you can also do multiple replicate. And finally, there's like technical variation from sequencing your sample, right? And we know it's usually like a Poisson process during the sequencing. So with so many variation already existing in DMS data, effect estimation DMS is like very complicated or hard due to small sample sizes. So people usually do DMS in the number of replicates of like 1 to 3, and they don't do like a lot of selection rounds. Probably like 1 to 3 is the like the maximum like you can get. And there's the problem with this sample size is when your sample size is very small, your effect is not very stabilized. And here you see that only when your sample size is like more than like 20, your variance estimate start to get stabilized, right? But if you only do like 3 replicate with 1 selection run, you only get like 3 or 4 sample size, your variance is not stabilized. And it becomes a problem in hypothesis testing, right? Because you are going to get high uncertainty of variance estimate on the effect of each variance. And that will lead to low statistical power, which means that the variant you want to find, which is the gain of function variant, the loss of function variant, will be falsely labeled as neutral. So that's the motivation. And now we know that this is how we do DMS. And it's already like a very like huge screen. It's like a huge improvement from the previous experiment. And how can we improve the variance score estimate based on that? So when I first look at a DMS heat map, I realized that the neutrino scans inherently have a lot of structures. Right, just based on this heat map, which is the MET kinase domain, we have a few observations. So the first observation is that the mutations at the position residual are often correlated, right? You often see there's a residual that's completely neutral, which is white here, right? Or it's like completely loss of function. It means that the residual is like functionally very important. And also, despite being correlated, some substitution will behave differently, right? And this is often due to like amino acid substitution, like local context event of that residual. Right? And Rosace assumes that mutation within the same position are correlated. So what does it mean, right? How do we build it into the model to improve statistical inference? So now we assume that the prior of the variance score would be a normal distribution centered at the position score with some variance. Okay? And we can build this using a Bayesian hierarchical model with the assumption. Okay? So hopefully by giving more information into the model, we can achieve better performance at the effect size estimation. And what is a Bayesian hierarchical model, right? If you are not very familiar with Bayes, I often think that Bayes would be a tug of war between your prior and your observation. So when your number of observation becomes larger, your observation are given more weight. So the prior will have weaker inference to the final Bayes estimate, right? But if you're like, you only have like 1 or 2 observation, your prior will have like a more larger effect on your final estimate, right? And this is good because we like, this is how we incorporate the prior information into the model. And Rosace is more complicated than that because we don't set the prior, like we don't set the prior, like for example, to be 1, to be -1. We also learn the prior through the data. So I would say that the Rosace is a tug of war between the position mean and the data, right? Again, on the left side is our observed functional score. You can think of it as just doing a naive, like linear regression or like fold change on your variant in the data. And the left side is the first, like the pink one is the position mean. And that position mean, which is the price, also inferred through the data by the observed functional scores at the same position, right? And your final Rosace estimate will be a tug of war between that naive log fold change with the like all the other score at the same residual. So they're like sharing the information across each other through one position. And in the paper, we try to prove that by using this method, we can have lower false discovery rate while maintaining high power. So we use this example of OCT1 cytotoxicity data, and this is like a very classical plot of capturing the false discovery rate of your method. So look at the x-axis here is the rank variance by hypothesis testing. You can either rank it by hypothesis testing, which naively just a p-value, or you can rank by effect sizes. And the y-axis is the percent of synonymous mutation caught, which we use as a proxy of false discovery rate. So think about what an ideal curve would be, right? So you want your curve at first to be completely flat because you are calling out all the signal variance or your loss of functional gain of variance, right? And then this curve will be gradually increasing to 100% after all your signal variance are called, and you are essentially start to call the neutral variant. Right? And here we show that even with the number of replicate only one, Rosace could robustly control the false discovery rate by like more towards this ideal curve. Okay. While maintaining high power, right? There's like a few variants validating the paper by other kind of experiments, and we show that even it can control, like even though it control the false discovery better, it also have like maintained comparative power of calling out significant variance with other methods. And we've done like a lot of simulations of the DMS, and I think like they also have value like in determining like a lot of like experiment parameters. So like check the simulation results in the paper. Okay, and that is some like previous work we did on Rosace, and here I think it's like interesting for me to give you an insight section on how we can normalize and compare the scores across screens. I think it's very important because you see there's like a lot of like multi-phenotype or multiple condition screens design in the DMS right now. And it's like important for us to think about how we can compare scores. So yes, multiple condition, multiple phenotype design is common in DMS screens. So here I differentiate between those two. So the multiple phenotype would be that you're using, for example, different kind of assay to measure two different facet of the protein. For example, I use the example here's like the ddPCA, where you have the abundance of the protein and you also have the ligand binding of the protein. While the multiple condition screen is more about, okay, you have different ligand concentration or you have different ligand, but you are measuring the same phenotype. And I'm going to give you an example of multiple condition DMS, which is this new paper we just uploaded, Gabby just uploaded to bioRxiv about how to identify inhibitor-resistant mutations of the MET receptor. And in that paper, Gabby did 12 different DMS, one in the DMSO condition, and the other 11 would be 11 different inhibitor. And we measure the cell growth, like a kind of like using like DMS growth screen to measure whether the function is like responsive to the inhibitor. Okay, and now the question is that how do we identify inhibitor resistant or inhibitor sensitive variants from the DMS data? Okay, so suppose we know everything, like we are the god, we know exactly how the cells grow. So before we have, like, for example, we have a neutral variant and we have a resistant variant, right? We know the cell grows exponentially, so we measure the cell doubling rate or log change to a constant, which we call beta tilted. And also we do the same experiment in a inhibitor condition. And then we're going to compare between the growth rate of the MSO and the inhibitor, right? If during the inhibitor condition, the virus grow faster than the DMSO condition, we would think that this would be an inhibitor resistant variant. right? If they grow the same, it's not responsive to inhibitor, it will be a neutral variant. So that's how you see that identify these resistance sensitive variants require direct comparison of growth rate across conditions. Here I define the statistical delta, I call it delta V, which is your beta inhibitors minus the beta DMSO. And if this delta is larger than 0, it is inhibitor resistant, and smaller than 0, it is inhibitor sensitive. Okay, so this is the setup, right? And in the reality, like when we're doing experiments, we are still asking questions which mutations are resistance sensitive. I suppose we all we still have this very simple example of a neutral variant and resistant variant. And for DMSO, we see the cell doubling rate is 2, right? And for the inhibitor condition, this resistant variant cell grows slightly more than the DMSO, so it's 600 instead of 400. And we compute the proportion because during the next generation sequencing, we can only get a proportion instead of the actual cell count. Right? And we compute the fold change. You see that this purple variant, the beta V inhibitor is 1.2 minus 1 is 0.2, is larger than 0, so it is inhibitor resistant. Right? But what about this green variant? Right? Because we are only measuring the proportion, right? In the next generation sequencing, this green variant, this neutral variant will actually be shown as inhibitor sensitive, which is not something we want in the DMS screen. So that's why people, instead of using total count normalization, people sometimes, a lot of people use wild type control, synapse mutations as a control to normalize the data. So I call it the new gamma statistics difference in difference, right? We are computing the difference of inhibitor and DMSO, and also we are computing the difference of your variant of interest with the wild type control, synapse mutation control. And now we define this new statistic, we can say that if this gamma is larger than 0, it means that this variant is more resistant to inhibitor. Right? If it's smaller than 0, it's more sensitive to inhibitor. Okay. So now instead of fold chain, we calculate this normalized fold chain by wild type. Notice that we didn't use the log here, but we should use log. We're going to use log in the next example. And now the neutral will be 0 minus 0. You still get 0, so it will be a neutral variant. And this purple is still 0.4. So we identify this purple variant to be resistant. Okay, and now we're going to see a more complicated example. So again, we have this neutral variant, resistant variant, but now we add a wild type control in the experiment. Okay, yeah. This is something we learned from the last example that you need a wild type control. Okay, in a DMSO, it grows to some number of cells and also an inhibitor. Notice that here, this neutral variant is not exactly the same as the wild type. Right? You notice that this loss of function in the DMSO condition, right? It's not growing to 400 as the wild type is growing to 200. Right? But notice that it is the same loss of function as the inhibitor. So even though it shows both loss of function in the DMSO, in the inhibitor, it is an inhibitor neutral variant. Right? And that's why we compare between different screens. Okay. And for this purple variant, it is loss of function in DMSO, but it is neutral inhibitor. So, right. So that means that when we add inhibitor into the cells, it actually grows faster. So it will be an inhibitor resistant variant. Okay. And we're going to make it even more complicated, right? So you know that when you're doing different screens, you have you sample at day 0, you sample again at day 2, you sample again at day 4, right? But here, like, let's just say that the unit time growth is actually different, right? And this is exact like especially true in like these like kind of like inhibitor screen, right? Because you need to compute the volume of the inhibitor you add into the cells beforehand. If you add it like if you compute it wrongly or like you don't control the growth time correctly, like you're going to have the situation that the unit time is different. So now instead of like having 400, 200, 400 inhibitor, the growth time is larger. So you actually get 1600, 400, 1600. Right. And we still compute this like gamma statistic, which is normalized log fold change by the Y type. And you see here that this neutral variant now would be very inhibitor sensitive. I think like a negative 0.7 is like enough for us to call it as like inhibitor sensitive, right? The Y type is still neutral, the purple is still inhibitor resistant. But again, we have this issue with the neutral variant. Right? And it's a sign that shows that the synapse mutation alone or the Y type control alone are not enough for you to compare between screens. Okay, that's why we actually need negative control. People usually use stop codon, and assuming that the most deleterious mutation should have similar scores across inhibitors. So just think about it. We are not aligning like one point of two distribution. Now we are aligning like we have 2 points, so we actually could control the range. So we have one Y type, one like negative control the stop codon, and that's how we actually set up the measurement scale between like and to normalize it across different grades. And I call it a difference in scale of difference. So this new gamma statistic, which is looks a little bit more complicated, but it's like the idea is just difference in scale of difference is very simple. And the beta here will be the log fold change from the sequencing proportion, right? And again, the gamma, when the gamma is larger than 0, it means it's more resistant inhibitor. And when gamma is smaller than 0, it's more insensitive inhibitor. Right. And now we compute the statistics. We're showing that, okay, the Y type's neutral. Now this green variant becomes neutral. The purple one now is inhibitor resistant. And the blue one, the stop codon control, which is the control we add into the screen. Now it's also neutral, right? Because we know that the deleterious variant is going to be like behaving the same across screens. So my message here is that we actually need to anchor variants to compare non-reference conditions. And what people usually use is that the negative control is non-mutation. Oh, I think I typed it wrong here, but it depends on depending on what you define as negative, right? You need 2 controls. Usually it's non-mutation or Y type, or like the slope codon. And like statisticians, like we cannot magically produce controls without experimental data on anchor virus. You have to make some sacrifice, or you have to make some assumptions in order to align the data. Okay, so this is my conclusion slide. Statistical inference is important for diminution of scanning strains. And in Rosace, we employ position mean variance shrinkage to improve inference performance. And for a lot of multiple condition DMS, we need at least 2 controls to directly compare between the schools. And this is our tool. If you have time, please give it a try. So that's GitHub. It's built as an R package. So yeah, it should be very easy to use, and there's tutorial. And finally, I want to thank my lab, my UCLA colleagues, and also like my collaborator, Willow, Quality Maestas lab, and also Fraser lab from UCSF. Thank you so much.
Thank you so much, Jingyou. That was a very good talk, and it's a very important project that you're doing. And while we wait for the chat to see if there's any questions in the Q&A, let's see, not yet. We have some questions from our group. So from Mateo Cagiada, he's asking, could using the mean for each position and the variance in the low replicas regime hide possible variants that are out of the distribution because they have a different real behavior? For example, we have an experiment with only 2 replicates. What would happen if in one position, almost all the variants are loss of function, but one is a real gain of function? Will it also be classified as a lot of function? Because Rosace assumes all the mutations in one residue should behave similarly, right?
Yeah, so this is like a critique that we receive a lot, either during the review or during like all kinds of presentations. So during the review process, we try to address this question. So we actually do a scatter plot of the Rosace mean with, like, for example, the enriched 2 mean, or just doing like the naive log change. And we show that Rosace, the change of Rosace estimate is not actually on the mean. So your mean estimate will still have like 99% correlation with the other method, but its strength is at uncertainty estimate. Right? It's actually changing your variance estimate a lot. And for example, here that one consequence of your gain of function variance that the mean will still be like gain of function, but your variance estimate is actually larger because all of the variance at the same residual is loss of function, right? So it might be possible that you will classify this variance as neutral because you get a wider variance estimate. But I think if you're just looking at the mean, you will still get it as a gain of function.
Okay, yeah, that answers the question. And I have one about the normalization of scores across different conditions and different MAVs. So are there other ways to normalize scores across conditions without the cell growth rates? For example, for past experiments where only variant frequencies were detected, there are synonymous, there are nonsense and wild type control, but are there any additional experiments or analysis that we could use to normalize different experiments with the same variants?
I mean, of course, you can use, like, if you make different assumptions, you can do normalization. For example, I see people aligning the peak, right? Aligning peak of distribution because DMS usually bimodal, and some people align the peaks. And yeah, you just need to like make at least 2 assumptions in order to align your data. Yeah, of course, there's different way.
Sorry, the 2 assumptions would be?
For example, like your neutral peak would be like peaking at the same. For example, the mode of the neutral peak will be the same, and the mode of your loss of function variant is the same, right? This could be one without like actually putting the control in the experiment.
Amazing. Are there any other questions? Anyone in the chat? If you want to speak up as well, you feel free to do so. Let me see the Q&A. Yeah, I believe we don't have any more questions. So thank you so much, Jingyou. That was amazing.